Hello.
My name is Ayan George. I've been programming for a long time. I've been doing backend, programming since the mid '90s. Like my first job in the industry was at one of the first ISPs in the Southeast. And so, it's kind of like the ultimate sort of back-end type stuff. We're dealing with mail servers, web servers, that kind of thing. I'm getting a little bit ahead of myself. I just had a couple questions before, or a couple things before I start. First, I was wondering, who in here has used Go? Oh, sweet. Wow. This what's this mean? Kind of, sort of. All right, so not many people. I run the local Go Meetup, and what I find is that the community is kind of small. Can everybody hear me okay? Is this good? Okay. And what I'd like is for everybody who raised their hand, please come out to the Meetup. We do meet the third Monday of every month. Also, unfortunately, I didn't put my Twitter handle here, but my self-esteem is directly related to the number of Twitter followers I have. So what I'd like you to do is search for me on Twitter and follow me, please, because I don't have many followers right now. Also, thanks for the beer. It's a bad time to start drinking again, but here we go. Yeah. So, I've been programming back-end stuff for a while. I used to think in C. My background's in C. Let me change my slide intro. Whoops, ahead of myself. So yes, I've been programming C, doing back-end programming for a while. I remember back in the good old days where kind of the unit of like processing was the process in Unix, right? And so communicating between processes was, kind of expensive. Writing to a file, using Unix domain socket, or using like System5 IPC. What that required was basically a context switch. The kernel had to understand or had to be involved in that communication. And so what came about in like the mid '90s was POSIX threads, right? And so a lot of operating systems either had like user space implementations or kernel implementations of basically a lightweight process. And what that did was that eliminated the context switch for communication within that process, right? Because the process shared memory. It was a simple matter of like passing memory back and forth. You might have to like think about mutexes and that kind of thing, but it was a much lighter weight process than communicating between separate processes. And so around that time, again, I worked at an ISP, and so we ended up having to scale up. We were handling more customers, that kind of thing. And I became aware of a web server called Navis server. And this was like the first multi-threaded web server, really ever. AOL bought it, and they renamed it AOL server. But I was real active, they open sourced, and I was real active in the AOL server community. And again, this was a multi-threaded web server. And so why was that interesting? Why was that interesting to like AOL? Well, so AOL used to send out these like CDs, and you get them in the mail, and your grandma would put them in her computer, and it would dial up to AOL, and the thing would hit their website. And so there's one of the first companies that had like really big or really that had really kind of high demand, servers. And so what they realized was that in order to get the best bang for their buck out of their infrastructure, their software had to be more efficient. And so they purchased Navis server, which was able to handle more connections. And so also in my career, I worked on like large email systems. One was called like Intermail, and it was multi-threaded as well. And it had the same kind of, reason for existing. You had large ISP. We dealt with a lot of email, dealt with a lot of concurrent connections. And so we needed an efficient program to handle it. But what I found was that a lot of these programs that use POSIX threads were sort of niche, right? And it wasn't really common for people to think about concurrency or think about parallelism, unless you like really, really, really had to. And so in my career, what I've noticed is that typically businesses make the decision to either hire programmers who understand concurrency and threading, and doing it without like race conditions or what do you call it? Give me another concurrency problem. Race conditions and deadlocks. Thank you. That's what I was thinking. So either you could hire somebody who could do this, right? Or you could just buy more servers. And I think the decision a lot of companies made is just buy more servers, right? And so part of this talk is, or really kind of ultimately the goal of this talk was to explain how Go kind of lowers a barrier to entry. It makes thinking about concurrent problems easier, and therefore makes it a good language to apply to modern server or modern backend problems. Basically, you don't need to. It makes it easy enough where you don't need to hire $200,000 a year programmer to do it properly. What's that? Darn, I know, right? Yeah. Maybe you could probably make $200,000 a year programming Go. Not many people doing it yet. I had like a long spiel to put on this page, and this image had a little bit more context, but this is kind of like how I imagine sort of the average like back-end programmer. Maybe the big difference is that I usually keep my shades on when I'm like coding and doing cool stuff. She takes them off. And I Googled for like the average front-end developer, and this is like the first thing that came up. I'm sorry, any front-end devs here. But yeah, so. All right, so Go, enter Go. I've been programming Go for a while. I run the local Go meetup, as I mentioned. Some of the interesting things about Go is, to me at least, is the provenance of Go, like where it came from. Go was developed at Google by Ken Thompson, Robert, I'm going to mangle his name, but Samir, at Google in around 2009. There should be at least one name that everybody in this room recognizes in this list. Ken Thompson? Anybody who doesn't recognize that name? I'm just interested to, is anybody afraid? Really? Okay, so, is it really? Oh, thank you. Here's another thing. I'm terrible at spelling. I kind of just sort of write once and I don't really edit. So there's going to be tons of like spelling and errors and typos. Is it consistent? Gotcha. Okay, so oh man, I need to change that like right now. Okay, so Ken Thompson developed the B programming language, which led to the C programming language, designed and implemented Unix. One of the people developed Plan 9. Also invented UTF-8, or was one of the co-inventors of UTF-8. Of course, Rob Pike, another Bell Labs alum, Plan 9, Inferno, Squeak, New Squeak, UTF-8. And Robert Griesemer worked at Google, V8 high-performance JavaScript engine. That should be interesting to some people here. He's distributed computing expert, object Oberon programming language. If anybody used to have an Amiga, like Oberon and Modula 2 used to be real popular. I'm dating myself, I guess. But one of the interesting things that came out of this was on Rob Pike's Google Plus page. He had like a thread that describes the history of Golang. And one of the things he included was kind of like some of the initial emails that he and the other developers exchanged. And one was starting point C, fix some obvious flaws, remove CRUD, and add a few missing features, which I think is really interesting. As a C programmer, I find that that really rings true. The more I use Go, the more I feel like it's kind of a refinement and an improvement on C. But we'll get into that. So here's a Go family tree. I don't know if you could see that. There's a couple of typos in there as well, but at least one. But what I tried to do was show the lineage of Go, at least the languages that influence it, but also the people who influence, or people who developed some of those components that influence Go. And so in green, you have Rob Pike, who developed New Squeak and Squeak. You have Robert Griesemer, who developed Oberon 2, and you have Ken Thompson, who did everything we did, use today. And so, as you can see, those three people actually were involved a fair amount in the sort of lineage of Go, or kind of the what do you call it? Anyway. And so this chart isn't to scale. Go has well over 50 years of computing history sort of baked into it. if you add up like the total experience of the 3 developers, it's probably well over 100 years. If this chart was to scale, the top would be here and the bottom would be probably on the first floor or something like that. So what are the cool things about Go? Go is compiled and self-contained. So it compiles to your chosen architecture. Typically, the binaries are statically linked. Sometimes, depending on what you do, you might have like 1 or 2 runtime dependencies, like libc. If you don't have libc on your computer, then something's seriously wrong. Therefore, you don't need like a runtime to deploy. You could just take a binary, put it where you want it to be, and execute it. That's probably new and refreshing to people who use stuff like Node or whatever else. It's a simple language, only 25 keywords, and it's very C-like. It has concurrency baked in, so keywords, types, and control structures specifically for handling concurrency. And it has an extremely rich standard library, so built-in high-performance HTTP server, JSON and XML parsing, etc. It has garbage collected runtime, so that completely frees you of having to think about like memory well, it doesn't completely free you of having to think about memory allocation, but it removes a lot of the burden of thinking about allocation, especially if you come from C. That's really refreshing. And finally, it has rich tools for everything. One of the problems with C is that it was well-defined language, but the tools for it weren't very well defined. So what you ended up with was kind of a hodgepodge of whatever was available on your operating system or platform. So make on one operating system, CMake on something else, or whatever the Microsoft tools are, that kind of thing. But Go actually solves all those problems. Let's see. On the next slide. So here's a strongly held opinion. It's my opinion. I've stated this to somebody before, and they politely tell me I disagree. So I'm going to completely own this one. This isn't, this isn't necessarily like the truth. But if there's one thing to understand about Go, it is that Go is a programming language with the notion of concurrency baked in. Special syntax and types allow you to build concurrent algorithms that are easy to reason about and easy to scale. The biggest conceptual difference between Go and other languages is that it allows you to think about concurrent algorithms to solve everyday problems. And this is kind of a central feature to Go. Like, just like any other language, I mean, Go has basic kind of control structures, additions, loops, and all that stuff. So all languages like overlap a lot. But every language you think about, or every language you can name, has like kind of like one distinguishing feature. And I'd say concurrency is like the big distinguishing feature in Go. And I realize I'm like going on a lot, but I will eventually like do live coding, and this is gonna get a lot worse. So just hang on. I promise we're gonna do some other stuff. So just like lists are central to Lisp, objects to C++, stacks so forth. Pick another thing. It's like PHP. Whatever it is that's central to PHP, I don't know yet. Somebody please explain to me at some point. But like, concurrency is a thing that's integral to Go. So why are concurrency and parallelism important? All right, so I actually found CPU speeds, or actually kind of like it was on Wikipedia. It was all the Intel CPUs, turned it into CSV file, piped it through GNU-plot. If you guys want to see the source, it's awesome. I would love GNU-plot. So what I did was I plotted the CPU speeds from everything from the 4004, 8086, all that stuff, all the way to the current CPUs, and plotted a trend line through them. And as you can see, CPU speeds kind of like leveled off. And I realized Intel just recently sort of announced a 5 gigahertz CPU, and I think that would have like skewed it up a little bit at the end. But without that, you can see that we're actually kind of trending downward when it comes to CPU speed. But I took the same data and plotted the number of cores per CPU. And obviously from like all the early stuff, he had 1 core, but like around 2004 or so, what we started seeing is like multi-core processors. And so the number of cores are actually trending upward almost exponentially. We have like modern Xeon machines that have like 24 cores or something like that. And so Go addresses modern problems. The best way to squeeze more performance out of a system is to utilize more cores. We don't have more like cycles to work with. And so to utilize more cores and utilize concurrent algorithms that can be executed, hopefully in parallel. What's that, Mike? No. Well, so another thing I wanted to say is that you're welcome to interject and correct me. And because part of this is learning experience for me. And so please feel free to like ask questions or make corrections as I go along. All the cores? Okay, all right. I respect Mike, and so I was afraid he was like criticizing me. Yep. Okay. All right. So long as you weren't criticizing me. Okay. All right. So how does Go make concurrency easy and performant? So part of it is in order to execute a concurrent thread of execution, Go has a Go keyword, right? So that's as much special syntax as you need to start a concurrent thread of execution. Hopefully later I'll show how other languages make it a little bit more difficult. Go routines are very, very lightweight. Only 2K stacks. Context switches are very, very lightweight. Very, very, take very little time. And so I was talking about context switches earlier when it comes to like context switches between kernel, between user space and kernel with system calls and that kind of thing. So in Go, they've been able to tune it so that context switches between Go routines takes a matter of nanoseconds, right? Go routines are cooperative. So if one blocks, let's say on a system call or on a read from a construct called a channel, which won't make sense to you right now unless you program in Go, a Go routine can cooperatively say, you know what, I'll just park myself until this IO is ready. And at that point, the runtime can actually reallocate the resources for that Go routine to do something else. You could even reallocate it to do garbage collection if it needs to. And finally, Go actually provides primitives for communicating between Go routines, channels. Between Go routines. And an example of those are channels, select, range. Which again, I'm not trying to teach Go. What I'm hoping to do is like get you guys interested enough to try it out. So some of that might not make sense. I'm forgetting something, but I'm going to move on. So I conducted a little bit of an experiment on ODevs in the general channel. I asked if somebody could just write a program for me, just write a short snippet. And the program was a web scraper. What I wanted to see was what methodology most programmers would use to fetch a web page, retrieve the title from the web page, and return a list of the titles from the web page. And the idea is that the function would take kind of a variadic list of URLs and return a list of titles. And really, the title part was kind of a MacGuffin. Really, I wanted to see whether or not they would do it concurrently. And what I found was that this is a Python program, brilliant programmer. Some of you guys may even know him. He works for Amazon now. But his first pass was kind of a standard like sequential thing. PHP, so, it is what it is. It works, but it's another like standard sequential thing. Yeah, I know. I feel the same way. That's how I look at all PHP programs, though, not just this one. I do the same thing. One person wrote a JavaScript approach and actually used concurrency. And I thought there's some interesting things in here. But out of the people who did give me an answer, 2 people gave me a concurrent solution out of like I think 9 people, and I think the rest of people thought like I was trying to get them to do my job for me or something. But the 2 people who did concurrent approaches, one of them is over there. His name is Dustin. He's co-organizer of the Go Meetup. So he's exposed to Go. He has that lump that Go puts on your brain to write concurrent algorithms. The other person, I interviewed him for a Go job, and he knows Go. So I don't know whether or not these people would have like written a concurrent algorithm before having been exposed to Go. And it is an interesting coincidence that the only 2 people who returned a concurrent algorithm were people who use Go. So that supports my hypothesis that that's the lump, or that's the thing that Go puts on your brain. So, and I just gave the conclusions. And so the next part of my talk will be a little bit of live coding. What I'd like to show off is a couple of programs and how to leverage some of the primitives and tools that Go to optimize them for multi-core computers. I guess something else I wanted to say is that one of the most interesting things I found is I used to work with like Solaris machines, and I used to get really excited about like multi-processor hardware. And now every computer you have, like you can't buy a computer that basically isn't symmetric multiprocessing machine, right? Like my laptop has 2 cores, 2 hyperthreads per core, so basically 4 sort of logical CPUs. Nowadays, most people have like 8 in your like fancy MacBooks. So that's it. So I'm going to switch to some live coding. I'm going to have to like reconfigure my window manager. Just give me like 1 sec. But what I'm going to go over is kind of like a brief introduction to the Go command so that you guys aren't like freaked out by some of the stuff I do. Show an example of optimizing an IO bound, or well, not necessarily optimizing, but I want to show an example of an IO bound problem that we can solve with Go. And then I'll show an example of a CPU bound problem that we can solve with Go. They're all completely contrived, but hopefully you guys can apply these ideas to real world. Just give me a sec here. Okay, in addition to that, I don't want to go back into the present tool, so I'll just skip to the conclusion, and then we'll talk about, then we'll do some live coding. But really, ultimately, what I wanted to convey was that utilizing your hardware more efficiently saves money. I don't know how many people use like AWS or Google Cloud Compute. I've actually worked places where they're actually able to save money by optimizing their software. In some cases, actually switching to Go. I don't know if that's anyway. So it's by switching to Go. And so Go gives you the tools to write and verify that backend, not backed, software performs well on modern hardware. And Go makes concurrent and parallel programming accessible to all programmers. And so that kind of goes back to my example about like back in the day when you had to use pthreads, and it was actually kind of a difficult thing to do. Go makes it easy, so there's no excuse not to write performant concurrent software on modern hardware anymore. Oh, I'm sorry. I wanted to pick at somebody's code. Totally. That's one of the things I was missing. So here's a JavaScript, a concurrent JavaScript program. And this kind of illustrates some of the difficulty I think people have with concurrent programming. I hate to admit it, but none of this makes sense to me. I see like async, promises, await, and that kind of stuff. And I hate to admit it, but it feels like concurrency is a notion that's sort of shoehorned into JavaScript. And I think that's the case with a lot of programming languages, whereas Go was built from the ground up with concurrency in mind. So it's a lot more natural, and it helps you think about it easier. But I guess something I thought was interesting is that concurrency 5. Like, I wish I could ask him, like, where did he get that number from? Like, just 5. And so, like, there's no like hardware with like 5 cores. So I don't know. It's interesting. So here goes the bad part. Okay, so here I see this. All right. So the first thing I want to show is, I'll just go to this empty directory called example. Oh, it's not empty. All right. So this is a basic Go program. But what I wanted to show was that Go compiles to a statically linked binary that you can deploy pretty easily. But another interesting thing is that Go is written in Go. So if you ever have any like questions about how something works in Go, you don't have to do a context switch like to C or some other language when you're looking at the source. If I wanted to figure out how like strings were implemented or slices or maps or anything like that were implemented, I could read the source and think in Go in order to understand it, which I find is very helpful. More to the point, that's kind of like my go-to way of like understanding things about Go now, is just to read the source. In addition to that,
I could say go build. I'm running FreeBSD. I can say, well, first let's look at the Go tool. So Go tool, this list. This shows all of the operating systems and architectures that Go supports. This not just shows the operating systems and architectures that Go supports. This shows the operating systems and architectures that the compiler on my machine supports. So I could do something as simple as say, Go operating system. Well, let's look at that list again. So what's that? I can hear you. Let's do it. All right. So Go OS equals plan 9. Go Arch equals AMD. I don't know. It doesn't matter. 64. Go build. So now if we look at the directory, the file that it created was example 1, and we could try to run it, but I won't run because it's plan 9 binary. What's that again? Data. But let's try something. I doubt that's going to have anything interesting in it either. No, okay. Oh well. Trust me, it's plan 9 binary. If anybody has plan 9 installed anywhere, we can copy it and try it out. I just cross-compiled. But when you say cross-compiled, it's the meaning seems to when you think about cross-compiling with other compilers, it seems to be kind of like a chore, like kind of a thing. It's a pain, right? Whereas Go, it's natural. There's no. In fact, it's kind of. It has the capability of compiling for any architecture that it knows about, and it just happens to use the current architecture by default when you run it. So it's I almost don't think about it as cross-compiling. I made fun of front-end developers earlier, but let's list dist again, and you'll find something interesting in there. There we go. JavaScript WebAssembly. I actually started playing with this today, and it is like crazy awesome. And I might start doing front-end development with Go because you can actually compile to WebAssembly. It's pretty. I say fucking. It's pretty fucking awesome, right? So, I think that's really really cool. So what else? The Go tool is really rich. And we're going to delve a little bit more into that, but I feel like a little bit of time pressure. How are we on time? Okay, all right. I'm trying to move this along. All right, so the first application that I wanted to kind of like optimize was, again, an IO-bound application. And so my scraper is pretty similar to, what's that? Did I really? Oh, crap. This is killing me. Is it the projector or is it my? Oh, there we go. Awesome. Okay. I know he's intimidated it into working. I meant to delete some of this before we started, but let's see if I can salvage this real quick. Yes, I can. All right. So Go includes testing, like in Go. It doesn't prescribe like how to test. It doesn't say like you have to do unit testing, you have to do integration testing. It just gives you the capability to do whatever testing you need to do. So at least for this program, I'm going to use some of the test functionality to kind of exercise some of these functions. I don't have like a main loop or anything like that. And so that's one of the cool things about Go is that the first thing I typically do is start a test file and use that to help me exercise routines that I'm writing in a module. And so again, the task I gave people was to fetch the titles from a list of URLs. I wrote a little bit of the actual like HTML parsing stuff up here, but notice a lot of people use like libraries for that. So we're just going to focus on like this stuff right here. And so as you can see, oh, hold on, I didn't mean to. This is what I wanted to do. So as you can see, fetch titles takes a list of URLs, essentially iterates over the list, calls fetch title. If that doesn't throw an error, it appends the title that it receives to the list, and then eventually returns that entire list. And so most people would write that, you write that at work, you check it in, and you're like, awesome, I'm done for the day. You might go on Slack and be like, hey, who wants Chipotle for lunch? I just checked in my code, right? But as a Go programmer, that isn't like really like, this doesn't really like cut it, right? Because it's sequential. And so again, that lump that Go puts on your head is writing concurrent algorithms. So let's just benchmark this. I wrote a small benchmark here. That will not work because maybe let's do that. There you go. So if I write go test bench, and what bench takes is a regular expression that matches the function signatures of the test functions that you want to execute, you'll get this. It'll blow up because fetch titles are. Oh, okay. Yeah, I got a little ahead of myself there. Let's see. All right, there we go. There we go. So right now it's going out and fetching some URLs. I don't know what's going on with the network, but let's run this in verbose. That way we get a little bit more information. Ooh, one of the sites is complaining that I've been like pinging it too much, so it says too many requests. But so what that did was, what it tried to do is in a tight loop execute these fetching these URLs, and then kind of gives me like an average time. And so this is how many nanoseconds. I have no idea how to convert that outside of using what's the name of the Unix tool? Units. Let's see. So that's oh, hold on. That's in nanoseconds, and we want milliseconds. So that's about 1.4 or 1.04 seconds per operation. And that's how long it takes to get 1, 2, 3, 4, 5 URLs, right? So 1 second to get 5 URLs. And so again, most people would be completely okay with that. A lot of the people who implemented this program for me were perfectly fine with that. But in Go, we could do better. So I'm going to start by copying this function. I really feel like I'm running out of time. How are we doing? I'm good? Okay. So I'm going to change this function name to fetch titles sequential. And we're just going to remember that. And I'm going to add a test and have another one called concurrent fetch. And I'm just going to call that fetch titles. And this one's going to be called fetch titles sequential. All right. So we're going to write a concurrent title fetcher. And so in Go, it's pretty common to write a function that does the one thing you want to do. In this case, that function is fetch a title. And so what I'm going to do is I'm going to compose multiple fetch titles in such a way that I combine the results of them. So I'm going to go execute them concurrently and then compose them in such a way that I retrieve the results as they arrive. So let's see. It really doesn't help to have a Heineken before your live code. But let's see. So the first thing I want to do is, yes. So I'm going to create basically kind of inline static or an anonymous function. So I'm going to call it func. And I'm going to do that. What? What's that? What's that? Come on, Dustin, give it to me. Really? That sounds really funny. Come on, I want to hear it. No? Okay. So I give Dustin crap at the meetups, and I feel it now. I get it. So inside this function, I'm sorry. First thing I'm going to do is I'm going to create something called a channel. A channel is kind of a communication mechanism. It allows concurrent Go routines to pass information between one another. And so one of the things I want to pass is a string. That string is going to be the title for each call, for each URL. So let's call it title chan make chan strings. This is a little bit of optimization, but I'm going to make the backlog the len of URLs. Right? And so instead of simply reading the title, what I'm going to do is I'm going to check if there's an error. And if there's an error, on return. Otherwise, I'm going to pass the title to title chan. And so in addition to that, I'm going to execute this as a separate Go routine. And so that Go keyword before the function just means go do this. Go start a concurrent thread of execution and keep running. The best kind of equivalent I can think of is like if you're using Unix shell and you just put an ampersand after command. So it means immediately, or go do this thing and immediately return control to the main thread of execution. In addition to that, I'm going to have to pass a string to this. I'm going to pass our URL to this. So on the other end, I'm going to have to retrieve those URLs. So I'm going to say retrieve this title. So I'm going to say for title equals range over title chan. RC equals append RC title. So I'm going to be a little bit more bold, and I'm going to run this in a Go routine. And so now I need to introduce another concept called wait groups. Essentially what I want is I want to do something, but only after all of these Go routines have executed. So I'm going to go at the top. I'm going to include a package called sync. And I'm going to create a wait group. I'm going to say wait group equals sync wait group. And I'm going to add the number of work that I'm going to do in this wait group. And that's going to be the length of URLs. And then as each of these functions exit, I'm going to indicate that it's done. And so what this does is this wait group keeps a counter. And I'm going to use a function called wait group wait. And each of these wait group dones are going to decrement that counter until it's 0, at which point this wait group wait is going to unblock, and then this range part will execute. And so just now, we created a concurrent version of our fetch. And so what we're going to do is immediately spawn n number of HTTP requests, wait for the results, and as the results come in, append them to our list, and then return the list. Hopefully, if everything went well, I can compile this and it'll work. And also, hopefully, if everything went well, we could benchmark it right away. So go test bench, and we're going to run all the benchmarks, and of course, it blew up. So let's see what happened. Title. Let's see. What's this? What are you saying? Yeah, there you go. Thank you. What else? What else is wrong? Live coding. Undefined WG. Where is that? 74. Thank you. Thank you. There you go. RC declared not used. What's that? Yeah. Oh yeah. So Go is very strict. It's strictly typed. There's no such thing as warnings in Go. Everything's in error, including or importing modules that you don't use. So it won't let you do that. So RC is a string. There we go. A new variable. I declared RC somewhere else. Where's RC? There we go. Sorry, folks. This went way better when I was doing it by myself. If you can, just look away while I code, and that kind of makes me feel better, and I can probably do this a lot easier. So let's look at these benchmarks for each of these scrape techniques. And so here's the other thing that's probably killing my presentation is that the network's probably down, or my wireless card is probably died or something like that, because it's just sitting there, which means it's probably an error, actually. Let's see, where am I going wrong here? Wait. Yeah. Title channel. It's all arranged. Defer weekly done. Fetch title. Send title chain. All right, so here we want to wait. Once everything's done, we range over the title chain. Oh, here we go. So here's another reason we want to wait, because we want to close title chain. There we go. So the sequential fetch takes about 1.7 seconds. Concurrent fetch, still running. Oh no, there we go. So as you can see, it was actually able to execute it quite a few times, and it's saying it only took 3.47 nanoseconds per operation, which is completely wrong. That's something wrong with that. Close title chain. Oh, come on. I swear this worked for me. Yeah. There you go. Actually, yeah, something weird was going on there. This number is more realistic. But let's actually test it. Let's look at the output of we'll just create like a test. We'll call it concurrent. And so we'll call this fetch titles, and this is fetch titles. Sequential. So let's test run, and the regular expression we're going to give it is test con. Oh, let's run it in verbose so you see the output. So it's actually working. We just verified that the function works. So those numbers that we're seeing are real. Maybe there's some kind of like weird network thing going on. So let's run the benchmark again so I could actually demonstrate the advantages of doing this concurrently versus sequentially. Of course. That's wrong. Yeah, it's really fast. Maybe it's really doing that. Are you guys have some kind of cache or squid or something like that? It's actually working. I don't understand why. Okay, well, what I'll say is that I hope what I've demonstrated is that running is that what I've demonstrated is that here we have an IO bound problem that greatly benefits from concurrency. This is so weird. So it's saying that it actually ran it that many times. That's how many times that loop executed, which doesn't make sense. So another thing we could do is look at what the runtime is actually doing for that. Hey, Mike. It really isn't helpful. I was just being aggressively concurrent. But let's remove it. I can't think of a reason why that would affect things. But right. Ooh, it does do go. Let's see, go clean. So let's clean the test cache. That was a really good catch. That might be it. Possibly, but notice that. Yeah, I hate to admit it. I swear this was working earlier. I hate to admit it, I'm not sure why we're getting like 17.4 nanoseconds per operation. Oh, gotcha. So you can say test bench, and I could pass that as the benchmark to run. Oh, so that's saying 2.4 seconds. Yeah. Let's see. Run. Okay. Again, we have to move along, but I hope I did sort of demonstrate that running concurrently is faster than running sequentially. But that's kind of an obvious thing. What's that? Yeah. So the testing and benchmarking, these are built into Go. It's not like these are separate libraries or separate packages or anything like that. But in addition to that, let's see. So in addition to that, we could do profiling or tracing. So what I just did was I output actual trace log for the execution of this of that Go routine or that routine, and I could say Go tool trace out, and it'll actually fire up the browser theoretically. Oh man. There we go. Okay. And so here, I get an opportunity to look at the Go routines that were actually created during the execution of that function. And so a lot of the Go routines that it creates are usually there to service like system calls, like the DNS lookups, name resolution, actual like connections. So we see like TLS connections, and of course part of this was negotiation of like I use HTTP URLs, and so a lot of this was redirection to HTTPS URLs and that kind of thing. But the most interesting display is this. And this looks normal. This looks like what I would expect. And so these things along the left are the logical CPUs in my computer. And so, like I said, I have Core i7, Intel i7 with 2 cores, 2 hyperthreads per core. So I'll have 4 processors essentially. And so as we could see, the work was evenly distributed across our 4 processors. And we can show that I could set Go max prox to 1 and limit the I did not mean to do that. I could set Go max prox to 1. And then we could view that output. And look at the trace. As you can see, that limited the execution to only 1 processor, 1 virtual or 1 logical CPU, but it pretty much got the same performance. And that's because we probably would have gotten the same performance on like a VIC-20 or something like that, because the long pole in the tent is the network I/O, not like multiplexing between like the inputs or anything like that. So this is an interesting problem. We have a lot of gaps here. So if you imagine if you had a high demand or high load web server, then you could fill these gaps in with more requests. But again, this is an example of an I/O bound application that we optimized using Go routines. And I'm going to let you guys go after I show a CPU bound application that we can optimize using Go routines. I kind of struggled to like find like an applicable, like interesting application, and all I can come up with was like a Mandelbrot generator, and that's because
it has well-defined CPU kind of requirements, and I could do it in a deterministic way, like generate the same give it the same parameters and get the same CPU impact out of it. So it's pretty bog simple Mandelbrot thing. I kind of had a little bit of fun playing with it. Just to show that that it does something. I created a little web server for it, and what port did I say it was listening on? So here we go. It just generated that on the fly. And we were talking about like those ugly like get parameters. I could change stuff like width equals 2048 and height equals 2048, and it'll recompute it. So it's kind of did I mistype something? H-E-I. What did I misspell? Oh, O-D-T-H. So as you can see, I'm actually doing this. There's no like there's nothing up my sleeves. We're actually generating this Mandelbrot real time in the web server. But if we look at its execution, if we do go test trace, we're going to put the output into trace out, and then go tool trace out. Yes. I don't know. Yeah, like so you're just like you say, you're targeting your whatever WebAssembly implementation for your browser. So yeah, I have no idea, and I'm brand new to it, so I would love to know the answer to that. I'm really anxious to like go play with WebAssembly now that I've learned how to like build stuff using Go. So yeah, I'll have to just be honest and say I don't know. So of course, again, this was like the bog simple Mandelbrot generator, and as you can see, only one core is ever in use at any given time, and that sucks, right? We could do a lot better than that, and we could utilize the CPU on this machine a lot better than this. And again, the point I'm trying to make is that if you're paying for AWS instances or paying for like Google Cloud Compute instances, and your software is doing this, that's money you're wasting. That's resources that are just being idle, and Go allows you to actually utilize those resources. So hopefully I'll successfully refactor this. We'll see. So like a lot of other cases, we have one function. So after we compute kind of like the parameters, so we transform our x and y coordinates, and then we create our complex z, and we pass that to Mandelbrot, and that just computes the point for that x and y coordinate. And so Mandelbrot is nice and easy to parallelize, right? So what I'd like to do is start by hoisting this out, right? And so now what I want is to create a channel that has parameters that I can then feed to Mandelbrot, and then have the Mandelbrot function compute those, or compute the answers to those parameters in parallel, theoretically. So I'm going to start by creating a type called a param, and it's going to be a struct. And of course, we're going to need an x and a y, which are ints, and we're going to need a z, which is a complex on 128. And so another interesting thing about Go is that it's relatively high level, but it's also low level enough that you could think about types, and you could think about how types impact the performance of your software based on like cache performance, based on the size of the types that you based on the size of the structs that you compose of these types. So in this case, since I have a 64-bit machine, I know pretty sure that x and y are 64-bit ints. So I know that this portion takes up 128 bits, and I know for pretty sure that complex 128 takes up 128 bits. And so I could reason about like the details if I want to. They're not necessary, but it's just kind of an interesting thing about Go. So here I'm going to
let's see, I'll make a P, and it's a type param, and I'm going to stuff P y equals this. Whoops. Gosh. P x equals this, and P z equals complex x y. And so now I've built like a parameter to pass. Another thing I want to do is I want to create a channel. So I could say, let's call it like param chan, and it's going to be make chan of param. And I'm going to do a little hand wavy thing here, and I'm going to make the backlog or size of this channel, the dimensions of the image I'm trying to create. So I'm going to say m.height times m.width. If you guys want to have beers later and have me explain that to you, I will, but it's kind of outside scope right now. And so the first thing I'm going to do is I'm going to take this new parameter, and I'm going to send it to my param-chan. And so right now that's not very interesting. What I want to do now is read from that param-chan. So I'm going to say for p equals range over param-chan, and I'm going to say set px, py, pz. And like in the last one, since I'm going to run this concurrently, I'm going to create an anonymous function. I really want to know what Dustin said earlier. Okay. And likewise, I'm going to need to use a sync package to kind of coordinate some of this. So I'm going to say wait group equals sync wait group. And I'm going to add work. So wait group add m height times m width. I promise I'm almost done. And let's see. And after I send, hold on. I messed up. Just give me one sec. I'm sorry. I wanted to use a different model for this. So in this case, what I want to do is I want to spawn n number of readers for this. So I want to say go func here. I want to set a concurrency level. So for I equals 0, I is less than m concur. And see, and this is something I set up earlier. I added a field to our Mandelbrot type that indicated our concurrency level beforehand, and then I++. And so what this does is it spawns n number of Go routines that are waiting to read from our parameter channel and then set a point in our Mandelbrot. And so in our Go function here, or in our parameter generating function, we're just going to generate parameters, send them down the param-chan, and each of these are going to read. And so at some point, I need to close a param-chan, and so we'll do that here. All right, and so any of you Go programmers, anybody here, see anything I'm missing? Because I'm kind of anxious. Thank you. But it should be actually px, and that py. Yeah. Yeah. Thank you. Sorry. Yeah. So I let, yeah. Yeah. Thank you. Thank you. Anybody else got any?
Uh, complex should be fine, but we could do, just be clear, complex 128. Thank you. So this passes all the parameters, immediately does this. One more time. Yeah, that works. Oh, I see what you're saying. Oh, thank you. Thank you. Um, just give me a sec. Like I said, this worked a lot better when I was doing this at home by myself. What's that? Oh, okay. Sorry. So, all right, this is going as poorly as I feared. I promise we'll get this going. You know what? All right. Don't drink and code, everyone. All right. So, okay. Sorry. I happened to check out the version that I actually wanted to work. So I worked on this before. What I hope to do is kind of like live code, implementing this in a concurrent way. What I happen to do is check out the actual end result that I hope to achieve. I actually forgot that I checked it in. But this is good. This helps me. This helps kind of speed this up and kind of saves me from looking like too big of an idiot. So here we go. This is theoretically what I would have like coded on front of right before your eyes earlier, which is that I created a parameter channel. I created parameters on the fly, passing my parameter channel, created a rate group that waited waited for the parameters to finish coming through, and generate a Mandelbrot for each of the generated a Mandelbrot point for each of the parameters. So if I now go, let's see, go build, and let's verify that it still works. All right, so with these parameters, still generating them. Let's try tweaking the parameters just to verify that something's happening. Okay, so it's still doing something, still works. But let's look at the CPU profile, I mean the trace for it again. So go tool trace. So again, if we look at the Go routine analysis, we see that, wow, render actually, for some reason I used 10 Go routines. That doesn't really matter. But let's look at the actual execution trace. As we can see, my 4 cores are absolutely pegged out. And we see that the Go routines actually consumed every kind of free moment in the execution graph. And so, therefore, this is a lot more efficient. It executed a lot more quickly. In this case, you know, just a tad over 600 milliseconds. I think the last one was like over a second or something like that. I should have recorded it. In fact, did I save that old trace? I didn't because I'm an idiot. But so what I hope I demonstrated was that with Go, I can squeeze every last bit of performance and every last cycle out of the software that I write. And what this translates to when running in production, when, again, using services like AWS or even running your own infrastructure, if you have cycles that aren't being used, you're wasting money. And if you want to use a modern language that's well suited for this sort of thing, I think Go is a great choice. I apologize for how poorly I did with with my live coding. Hopefully, this won't dissuade you from trying it out. Also, if you're interested in seeing me fail like this even more, you can come out to the Golang meetup on the third Monday of April. That's all I have.
Questions for Ayan?
Any questions? Yep.
There's no what is quick explanation of its purposes? I didn't see it.
So what defer does is it adds code to the stack to execute at any point that it returns. So what it allows you to do is define code that you want to run whenever the function exits. So that allows you to define cleanup stuff. And so what I did was I kind of skipped deferring. It's kind of, I could have said like defer wait group done there, but it feels a little like overdone because there's only one place where this function exits, and so might as well do it at the tail end of the function. But defer has some interesting side effects or interesting kind of quirks, because what it does is it evaluates any parameters to the function before deferring it. So if I had like even defer at fumped printf hello, or whatever, %d(x) or whatever, it would actually evaluate x and then stash the parameters so that it could call the function with the evaluated parameters at the end. And so that causes some programs a little bit of confusion. So that's kind of an interesting gotcha when it comes to defer. Anything else? Come on, somebody. It's not a plugin. I use line numbering and then relative line numbering. So you have to add them both. So if I do like set no rel, it just gives you regular But if you so this way I can see where I am, but also if I wanted to like delete the next 9 lines, I could say like D9, and I see how far I have to go. So yeah. Please, somebody, give me a Go question. I hope I didn't like scare you away from Go. Everybody's gonna go back and be like, I'm gonna use Node now because that Go guy sucked, kind of thing. Come on, I need one more Go question, please. No, nobody.
What happens with the brace on the next line?
The brace on the next line?
Yeah.
Where's that?
Like on line 6. Move that brace down to the next line. Yeah.
Line 6. Okay, so this line.
No, that's the greatest flame word ever on the internet.
Okay. So
I think they fixed it.
Well, Go is very, very opinionated about how formatting should be done. One of the Go tools is Go fumped being short for format. And one of the best quotes I've heard about this tool is that it's everybody's favorite, or it's nobody's favorite, and that's why it's everybody's favorite. There's no options to Go fumped. It will format your code one way and one way only. And that answers or solves any arguments you might have about how to cuddle braces or how to indent your code and all that stuff. So, yeah, exactly. And so what would happen is that since I'm using, first, it's actually not valid to do that. It's a fatal error. But any other thing like that, like if I add like white space or if I format stuff in a weird way, I have a plugin that runs GoFump as I code. So if I write it, it's just going to like fix it for me. And
I know the answer to this, but I just wanted to like highlight something I really like about Go.
Okay.
Could you quickly demonstrate Go doc?
Oh yeah, thank you. That is probably like the most powerful thing about Go, in my opinion, because a lot of people will like Google for information about Go, but one of the things I recommend is learn GoDoc right off the bat, because as I code, I don't want to have to like switch to my browser. So what GoDoc does is Go has a formatting convention that allows GoDoc to extract documentation from your code. So if I want to see the documentation for, let's say, the HTTP module, I just say go, doc net HTTP. Oh, dog. And it gives me the documentation. If I want to know the documentation for any particular function, I can say go doc HTTP. Those are types. Let's look at functions. Set cookie. There we go. Oh yeah. Well, go doc net HTTP listen and serve. Right. So it gives me all the documentation right there. So I don't need to like go Google for anything. And it does the same thing for your own code, right? So like, let's say I have this function and I want to say Mandel brought prints pretty picture. I can say go doc Mandel brought. And it'll give me the signature and the actual documentation. In addition to that, it gives me documentation for any types that it uses. So as you're learning Go, what I recommend is learn GoDoc first, because it's the easiest and best way to kind of explore the standard library without having to like kind of context switch. You can stay in your code, stay in the same terminal, and still kind of learn more about it. I feel like I've gone way over my time.
Yeah, one last question. Hello. No? All right. Well, thank you again. Round of applause.